Welcome to the deep dive. Today, we are jumping into a subject that really underpins huge areas of modern engineering.
It really does.
We're talking about everything from designing jet engine components to, simulating the safety of your car.
Absolutely. We're looking at nonlinear computational mechanics, or NCM, and its inseparable partner, the finite element analysis method, FEA.
And for this deep dive, our main source material is an academic text by Bonet and Wood that really tries to unify the whole field.
That's the goal, isn't it? To connect the deep theoretical backbone of continuum mechanics to the actual computer code that engineers are using every single day.
Right, because the reason this all exists is, well, the real world isn't linear.
Not even close.
If you're dealing with metal forging, crashworthiness, or watching a bridge buckle under its ultimate load, the geometry changes so much, the deformation is just unrestricted, that all that simple linear math completely collapses.
It does. Linear analysis it's fantastic for small, controlled problems, but when you want to simulate a component under extreme loads, or, say, a material like rubber that stretches like crazy, the numerical tools from NCM are really the only practical way forward. It lets us get closer to physical reality.
Okay, so let's unpack that. Where does this nonlinearity actually come from?
Yeah.
Because it's not always about a material just breaking, is it?
No, not at all. The textbook really breaks it down into two main culprits, two things that push us out of that comfortable linear world.
And the first one is the most intuitive, I think.
It is. It's material nonlinearity. This is when the stress-strain relationship, the basic behavior of the material, is not a straight line anymore.
So you're talking about things like plastic yielding, where it permanently deforms.
Exactly. Or things like creep, or even just contact friction. The material itself is behaving in a complex, nonlinear way.
Okay, so that's the material side. What's the other big source? Is it something more subtle?
It's incredibly subtle, but it's so powerful. It's geometric nonlinearity. This is when the geometry of the body changes enough during loading that you have to include those changes in your equilibrium equations. The material could be perfectly elastic steel, but if it bends a lot, the direction of the load changes relative to the structure, and suddenly your simple equations are just wrong.
That's a great point. Let's make that more concrete. The book uses a classic example. A simple weightless bar connected to a spring, a cantilever.
Exactly.
In linear mechanics, you just assume the moment arm is fixed. But what happens when that bar rotates, say, 30, 60 degrees?
Well, everything changes. The vertical force you applied is now acting on a lever arm that's getting shorter and shorter.
So the relationship between force and displacement is no longer a simple constant.
No, it depends on the cosine of the rotation angle. The geometry is now controlling the response, not just the material.
And this leads us to some really high-stakes engineering problems, like stability. Buckling. The simple column example is a classic for this. Linear analysis can give you the famous Euler buckling load, but that just tells you when it might fail.
Right, it's a prediction. To understand how it fails, you need the nonlinear approach. And that reveals this amazing phenomenon called bifurcation.
Meaning there's more than one possible answer.
Yes. Past a certain critical load, the math shows that 3 different equilibrium solutions can exist at the same time. The column could stay straight, or it could be in one of 2 symmetrically buckled states. The structure suddenly has a choice.
And it can just snap into one of those other states. We see that in the truss example from the book with what they call snap-through behavior.
That's such a perfect visualization of instability. Imagine you're pressing down on a shallow arch or a dome. You increase the load, it resists, and then it hits a peak load, a limit point.
Okay.
If you try to add even a tiny bit more load, the whole structure can violently move its snaps through to a completely new, much deeper shape.
And critically, linear methods just can't predict that path. They just fail or jump to some other solution. They wouldn't trace the snap.
No way. They can't handle it.
So, if that geometric complexity is the why, let's get into the how. How do we even talk about motion and deformation when they're this large? This brings us to kinematics.
Right. Kinematics, the study of motion without worrying about what's causing it. And with large deformation, we have to throw out our basic assumption that the start and end shapes are more or less the same.
Which means we need 2 different frames of reference. The sources call them the dual descriptions. The first is the material description, or Lagrangian.
Yep. That's looking at everything from the point of view of the initial undeformed body. Your coordinates
body. the coordinate is x.
And the magical link between them is a thing called the deformation gradient tensor, F. It's a matrix that tells you exactly how a tiny little line in the original shape gets stretched and rotated into its new orientation in the deformed shape.
And this is where we hit that big aha moment. The reason we can't just use our standard linear strain calculation anymore. Let's use the test case. We take a simple 2D solid. We don't stretch it. We don't shear it. We just rotate it by 90 degrees.
A rigid body rotation.
So physically, the strain has to be what?
0. Of course, it's rigid. Nothing has deformed. That's just fundamental physics.
But if you take the displacements from that rotation and plug them into the standard linear strain formulas,
you get complete numerical garbage.
It's not just a small error. You get answers like -1 for the strain. The math is telling you the block has shrunk by 100%. It's vanished.
It's totally physically impossible. And it's because that simple linear measure just can't tell the difference between a real deformation and a simple rotation. It gets confused.
So the fix is to use a new tool, a nonlinear strain measure. The most common one is the green strain tensor.
Right. It's a mathematical formula that's been specifically engineered to give you 0 strain during a rigid body rotation. It cleverly accounts for the displacement gradients in a nonlinear way, so it successfully filters out the rotation part.
That's such a vital takeaway. The strain measure you pick isn't just a matter of preference. It fundamentally changes whether your answer is reality or nonsense.
And what's key is that all these different measures, linear strain, green strain, logarithmic strain, they all give you pretty much the same answer when the deformation is tiny.
But as soon as it gets large,
they diverge completely. They give you different numbers, but each one is physically valid in its own context.
Okay, let's pivot from motion to material behavior. Section 3 in the book covers 2 big categories, starting with hyperelasticity.
Hyperelastic materials are, you could say, memory-free.
Memory-free, I like that.
They're defined by a stored strain energy function. This basically enforces path independence. Think of a perfect rubber band. You can stretch it, twist it, compress it.
And the stress it feels only depends on its current shape compared to its original one.
Exactly. It doesn't care about the journey it took to get there.
That sounds computationally nice.
Oh.
But as we get into more realistic problems, like plasticity, we run into this issue of incompressibility. And that creates a famous computational headache, volumetric locking.
Oh, it's a huge problem in FEA. A lot of these large strain processes, especially plastic flow and metals, happen at almost constant volume.
So the determinant of that deformation gradient, J, should be 1.
Right. But if you try to enforce that constraint too strictly with standard finite elements, the math becomes too stiff. The elements just sort of lock up.
Like you're trying to model something flexible with a cage made of granite.
That's a great analogy. It imposes this artificial stiffness, preventing the element from deforming the way it should, hence locking.
So how do you solve it?
With more advanced techniques, like mixed variational principles. The key idea is you treat the volume change and the shape change as separate things. You decouple them, which stops the math from seizing up.
Which brings us to the really complex case, large elasto-plastic deformation. If hyperelasticity is memory-free, plasticity is all about history. The loading sequence matters completely.
It absolutely does. And to model this, we use a fundamental idea, the multiplicative decomposition of the deformation gradient. F equals F elastic times F plastic.
So you're conceptually breaking down the total deformation into 2 steps, a permanent plastic part and then a recoverable elastic part.
It's a conceptual trick, yes. You imagine an intermediate unloaded state. But here's the crucial insight. That stress-free state is only defined locally at a single point.
Right. Why can't you just reassemble all those little unloaded pieces into a global object?
Because plastic deformation involves slip and shear at the microscopic level. If you could magically undeform a piece of plastically bent metal, you'd find that the neighboring regions have permanent shapes that are just incompatible. They'd overlap or there would be gaps.
And that incompatibility is why it's path-dependent and it has to be calculated step by step.
Precisely. For each tiny increment of time, you calculate a trial elastic stress, just assuming for a moment that no more plasticity happened.
But if that trial stress is too high, if it's outside the yield surface,
then you know your assumption was wrong. Plasticity did occur, and the stress has to be brought back.
And that's where the return mapping algorithm comes in.
It is the absolute workhorse of plasticity simulation. It's an iterative process that figures out how much plastic strain occurred in that step and uses that to map the stress right back onto the yield surface, making sure all the physics is satisfied.
Okay, so we've got the theory of motion and the theory of materials. Now, section 4, the computational engine that pulls it all together, FEA.
Right. FEA takes the governing physics, the principle of virtual work, and it turns this continuous problem into a finite set of those nasty, nonlinear algebraic equations we've been talking about.
And you have to solve them iteratively. The go-to method is the Newton-Raphson method.
You're basically linearizing the problem at each guess. You approximate the complex curve of the solution path with a straight line, and you solve for a small correction.
You solve the system KU equals minus R. R is the residual, the out-of-balance force from your last guess. Here is your correction. But all the complexity is buried in K, the tangent matrix.
The tangent matrix is the computational heart of NCM. It's the instantaneous stiffness of the structure. And it has two essential parts. The first is the one you'd expect. The constitutive component. That's your material stiffness, Young's modulus, and all that.
And the second component. This is the real sign that you're in the world of geometric nonlinearity.
It is. It's the initial stress component, sometimes called the geometric stiffness.
And this is the part that's so critical to get.
Yes. The geometric stiffness has nothing to do with the material properties. It is a stiffness term that is generated only because there is already stress in the structure, and as the geometry changes, that force acts in new ways.
It's the stiffness from the load itself.
Exactly. If a column is already compressed and it rotates just a tiny bit, that compressive force now creates a restoring moment. That effect is the geometric stiffness.
And if that term becomes negative enough, it can cancel out the material stiffness and drive the whole tangent matrix K to zero.
Precisely. A singular, or zero, tangent matrix is the mathematical signal for buckling, for structural instability. It tells you the stability of your structure is fundamentally tied to its current stress state, not just what it's made of.
So powerful. But we said earlier that the standard Newton-Raphson method can fail. It has a flaw near those peak loads, those limit points we saw in the truss.
It will fail, absolutely, because near that peak, the only way for the structure to stay in equilibrium is for the load to actually decrease for a moment while the displacement continues to increase. A standard load-controlled method just can't find that solution.
It's lost.
Or it just jumps across to some other part of the curve, completely missing the unstable behavior.
So to trace that full complex path, to actually see the snapback, we need a better method.
We need the arc length method. This is a much smarter algorithm that treats the load and displacement as a pair. It adds an extra constraint that controls the total distance traveled along the solution path in each step.
So it's walking along the curve itself, not just pushing the load upwards.
Exactly, which means it can gracefully trace the path right over the peak and down the other side, even when the load has to decrease. It allows us to capture those violent, unstable snap-through events accurately.
It's an incredible synthesis when you see it all together.
That's the unification that NCM provides. It shows you that the kinematics, the material models, and the computational routines like Newton-Raphson and arc length, they have to be studied as a single interconnected subject.
Right. You can't just use a commercial nonlinear solver effectively if you don't understand why that tangent matrix has two parts, or why you need a nonlinear strain measure.
It separates someone just pushing buttons from an engineer who can actually interpret the results and know if they make sense.
Absolutely. And I think if we take one profound idea away from this whole deep dive, it's that one. The tangent matrix shows us that stability is coupled to the current state of stress and geometry, not just the material's inherent strength.
That's the core insight, I think.
Which really makes you wonder, doesn't it? When you look at any complex system, a thin plastic bottle, a giant crane, even the way bones and tendons interact in your body, what are the critical hidden initial stress states inside them that could suddenly transform their stiffness and trigger a catastrophic instability?
That's a great question to think about.
A challenging thought for the day. Our deep dive today was centered on the comprehensive treatment of the subject provided by Javier Bonet and Richard D. Wood. Go forth and analyze those complex nonlinear realities.